Your model just made a prediction, but which features actually did the work? Was it the debt ratio, the income, the length of credit history? Feature importance answers exactly that, and we'll measure it, not just assert it. Why should we care? For a few very practical reasons. It builds trust, it helps us debug a model that's leaning on the wrong thing, and it can reveal real insight about the problem. It can even let us drop useless features and build a simpler, faster model. Tree-based models hand us importance almost for free. Here's how. Remember that a tree picks each split to reduce impurity, to make the groups purer. Watch a split happen, and its impurity drop gets credited to the feature it split on. Add up those drops for each feature, across every split in every tree. A feature that did a lot of the tidying up scores high. Collect those totals and the model hands us a ranking. Let's grow the bars from the real trained model. Debt ratio comes out on top at 0.42, the model's favorite clue. Credit history is close behind at 0.35. Income and loan size trail far behind, around 0.1 each. In one glance, we see the forest leans on debt ratio and credit history, and barely touches the other two. But what about models that don't hand us importance, like k-nearest neighbors or a support vector machine? There's a beautifully simple, universal trick called permutation importance. Take one features column, and shuffle its values into a random order. That keeps the column's numbers, but breaks its link to the answer. Now rescore the model with that one column scrambled, and watch the accuracy meter. Our baseline is 81%. First, shuffle debt ratio. The accuracy collapses, down to 75%. That 6-point drop is the model crying out for a feature it desperately needed. Debt ratio matters. Now put it back, and instead shuffle income. Watch the meter, it barely moves, still 81%. Scrambling income cost the model nothing. So the size of the drop, when you break a feature, is exactly how much the model was relying on it. The magic is that this works for absolutely any model. Trees, forests, boosting, support vector machines, k-nearest neighbors, neural networks, it doesn't matter what's inside. If shuffling a feature hurts the score, that feature matters. Simple and universal. 2 quick cautions. If 2 features are strongly correlated, they can split the credit between them, making each look less important than it really is. And importance tells you what the model uses, not what truly causes the outcome. High importance is a strong hint, not a proof of cause. In scikit-learn, both are one line. A fitted forest exposes feature importances directly. And permutation importance works on any fitted model, measured on held-out data. Pair the scores with your feature names, and you have an instant, readable ranking. So feature importance tells us which inputs the model actually leans on. Trees give it for free through impurity reduction. Permutation importance gets it for any model by shuffling a column and watching the score drop. Next, we go one level deeper, explaining a single individual prediction.